Y'all, we are gonna talk about transformations of functions today. Let me tell you how times have changed since I was in school a million years ago. We did not have Google. We did not have DoMyHomework.com. We definitely did not have Super AI. By the way, please don't use that. I don't want to have to write you up. Super AI to do my work. We had to be able to quickly sketch, because graphing, there were two different categories. There was sketching and graphing was very formal, and you would use a fringe curve and fancy paper, and it was a laborious process, and you had to try to make it look as nice as possible. But then you needed to be able to sketch functions very quickly to understand what happens to them as they get bigger, in the middle, whatever you're working on. Okay, I know you probably don't care right now, but it was important. And so in your book, they call these toolkit functions, and I had mentioned in a previous lecture that they were in books in the inside or the backside cover. So here's the book. This is not one of the books that from my college, but this is a book that I taught out of for several years. So it was, it's right here on the back cover. So I could quickly look at functions and what they look like, the basic functions, and then see how they moved. Use these transformation rules to move them. So while this is nice for you to know, this is not do or die like it was for me. So that's how things have changed. So this says, given a function f of x, a new function, g of x, equals f of x plus k, where k is a constant. That is a vertical shift of the function f of x. All the output values shift or change by k units. If k is positive, the graph will shift up, and if k is negative, the graph will shift down. So you're literally, if you add 2, you just take every point and add 2, and move it up. If you subtract 3, you take every point and move it down 3. So this is the s of t. Well, the first one is s of t equals v of t, okay, without the 20. And then, so this is the value here. And then if they add 20, they just took every point on this graph and added 20. And that's a vertical. So that's if it's added on to the end of the function, it is a vertical. A horizontal shift happens when you put it into the function. So given a function f, a new function g of x is equal to f of x minus h, where h is a constant. It is a horizontal shift of the function f. If h is positive, the graph will shift to the right. If h is negative, it will shift to the left. So this blue is v of t, and then v of t minus 2 is everything moved to the left 2. Now this, if you notice, this is defined as a negative. So if this always does the opposite. This is plus 2, so it's going to go to the left. If it's minus 2, it's going to go to the right. So it's a little bit counterintuitive. So this says, this represents the transformation of a toolkit function f of x equals x squared. Relate this new function g of x to f of x, and then find the formula for g of x. Well, we have the toolkit function x squared, and it goes through the origin. So this looks like we picked up the vertex and moved it over to the right 2. So this would be g of x is equal to f of x minus 2. And if you wanted the equation, x minus 2 squared. All right. Given the function f of x equals the square root of x, graph the original function f of x and the transformation on the same axes. Is this a horizontal or vertical shift? Which way is the graph shifted and by how many units? So I don't normally sketch. I normally try to keep nice things on here for you, but this is how we did it in the day. I kind of feel bad for my professors. Not a whole lot, but a little bit for having to grade all my stuff done by hand, especially when I took vector calculus and I had to do everything in 3 dimensions, but sketch it by hand. Ooh, that's a terrible axis, but we're going to go with it. All right, so my graph of the square root of x, the sketch looks like this, right? And so this is f of x plus 2, and so that's going to be 2 units to the left. And I don't really have a, I'll use this colored pen. And so it's the same graph, roughly. Pretend like it's the same graph to the left too. So it's f of x 2 units to the left. Okay, so now it's kind of like patting your head and rubbing your belly at the same time. We can combine vertical and horizontal shifts. Okay, so how do we do that? We're going to identify the vertical shift and horizontal shifts from the formula, and then we're going to move the graph accordingly. I'm telling you right now, if I were you, I would go to desmos.com/calculator and do it on there. Check your work, or just do it on there. Okay, you don't have to reinvent the wheel, but that's up to you. I don't get paid from Desmos. I like Desmos. Actually, this book that I just showed you right here that I taught out for years, it actually uses Desmos heavily, and I really thought that was a good utility. So I know that this is the graph of the square root of x. It's going to be down 3 and to the left 1. And because I wasn't going to make you do this, watch me graph it. Here is the process in a nice graphic. So this blue one here is the square root of x, and then they moved it. They did the to the left one first, so they moved it to the left, and they removed it, and they moved it down 3. And this is your final product. So this, now they've given you a graph, and they want you to figure out what the formula is. So I know this is some form of the square root function, because it looks kind of like a curved arm, and it is, but typically our toolkit function starts at 0, 0, so I know it's up 2, and it's to the right 1. So this would be f of x equals square root of x. It's to the right, so it's got to be minus. So square root of x minus 1 plus 2. So now we can have reflections across the axes. Okay, we used to do really fun dances with this. If you were in an in-person class with me, we would dance for extra credit, because we can show how all these reflections, how we would do these reflections with our arms. So we can have a reflection across the x-axis or the y-axis. So a vertical reflection graph reflects it across the x-axis, and a horizontal reflection reflects across the y-axis. So if this is the original function, if I take this function and multiply everything in the function by negative, it will flip. So like this right here is your mirror, and it will be a mirror image there. And then if I put a negative x in for x into the function, then it flips this way. And so my mirror is here. This is my original function, and this is the mirror image. Alright, and that's what we just said. So given a function, reflect the graph both vertically and horizontally. How to do that? We're going to multiply all outputs by -1 for a vertical reflection, and that's going to be across the x-axis, or you're going to, or outputs, sorry, and multiply all inputs by -1 for horizontal reflection. The new graph is a reflection of the original graph against the y-axis. So this says we're going to reflect s of t equal to square root of t vertically and horizontally. So reflecting the graph vertically means each output will be reflected over the horizontal t-axis. So it starts at 0, 0. This is 1, 1. Now it becomes 1, -1. This is 2, 1.5. So now this becomes 2, -1.5. And you just keep going. So v of t equals -1 times s of t, or v of t equals -1 times the square root of t. Notice you have to do this. This is an outside change or vertical shift that affects the output s of t values, so the negative sign belongs on the outside of the function. Okay, so if we're going to reflect it horizontally, it means each value will be input value, so what we put in. So this started at 0, 0 here, starts at 0, 0 here, but now I have 1, 1. Now this will be 1, -1, so on and so forth. So because each value is the opposite original input value, we can write h of t equals s of -t, or h of t equals the square root of -t. Remember, we have domain restrictions with square roots. Okay, so we can have even and odd numbers, we can have even and odd functions. You're like, thank you very much, Amy. I didn't make it up, I'm just the messenger. Alright, so a function is called an even function if every time I replace x with -x, I get the same number. The graph of an even function is symmetric about the y-axis, meaning the y-axis cuts it in half. A function is called an odd function if for every input f of x equals a -1 times f of -x. And a graph is an odd function is symmetric about the origin. And it can be odd, it can be even, or it can be neither even or odd. So let's look at this. And I normally start with even, because then I can take this value and multiply it times -1 and see if it's odd, and if it's neither, then I write neither. So this says, is this function f of x equal to x cubed plus 2x even, odd, or neither? Okay, so first of all, it would be very unusual for this to have a 3 as its leading its degree and be an odd function. But sometimes it can happen, but it's very highly unusual. So I would, in math I don't say never, but I say probably not. But let's check for even. Let's just act like we don't know. So if that's true, then f of x should equal f of -x. So I'm going to go in here and I'm going to calculate f of -x. And I have, so every time I have an x, I replace it with -x. And I get -x cubed minus 2x. Those are not the same. They don't have the same signs, so they are not even. So now I'm going to check to see if it's odd. So f of x should equal a -1 times f of negative x. And we just happen to have that right there. So -1 times -x cubed minus 2x gives me x cubed plus 2x. Is that the same as my original? So that's the same. So this is an odd function. All right, so here's the picture of that function. And so when I said it would be symmetric around the origin, what I mean about that is that if I take this, my pin here on the origin, there's really no good way to show you this. Okay, here on the origin. So if I flip this, so basically 2, 1, 2, if I flip it that way, I'll get the same picture. So this, if I click here, it comes up with the original picture. That's what it means by being symmetrical around the origin. That's a very amified, dumbed down, not dumbed down, it's not dumbed down. In plain language, that's what it means. Alright, so now if we can, we can add, subtract, compose, shift, side to side, up and down, and they can be even, odd, and now we can squish them and pull them out. So we can stretch and compress them. So if I take a function, so if this black function here is f of x, if I multiply f of x by a fraction, I compress it, so I smush it down towards the origin. And if I multiply f of x by a whole number, I'm going to pull it, I'm going to stretch it on the vertical axis. I'm going to stretch it vertically. So here, given a function f of x, a new function g of x equals a of f times f of x, where a is a constant. It's a vertical stretch or vertical compression. If a is greater than 1, you'll stretch it vertically. If a is between 0 and 1, which that's code for a fraction, so fraction or decimal, and then if a is less than 0, if it's a negative number, the negative will actually reflect it, and then the absolute value of a will stretch or compress. All right. So given a function, graph its vertical stretch, we're going to identify the value of a, multiply all ranges by a. If a is greater than 1, it's stretched by a factor of a. If it's a decimal or a fraction, you're going to compress it. And then if it's a negative a, then you will reflect and compress or stretch. Highly suggest you check these on Desmos.com. It'll make your life a lot easier, make your tests go faster, make your homework go faster. So here, in the dark blue here is y equals x squared. If I put in a 2x in for x, then that 2 will give it a horizontal compression. So we made it taller and smushed it. Now we're making it skinnier and fatter, okay? Wider and more slender. And so if I put a whole number inside the parentheses of the function, it's going to give you horizontal compression. And if it's a fraction or a decimal, you're going to get a stretch. So it's going to stretch it out. So given a function y equals f of x, the form y equals f of b of x results in a horizontal stretch or compression. So like I said, if it's a whole number, you're going to have a compression. You're going to squish it and then if you have a fraction or decimal, it's going to compress. All right. So write a formula to represent a function. Oh, sorry. How to. Given a description of a function, sketch the horizontal compression or stretch. You're going to write a formula to represent the function, set g of x equals f of b of x, where b is greater than 1 for compression and between 0 and 1 for a stretch. So this is write a formula for the toolkit square root function horizontally stretched by a factor of 3. So if it's stretched, it's going to be a fraction or a decimal. In this case, it's going to be by a factor of 3, so it would be 1 over 3. So if originally it's square root of x, then f of x would be x, the square root of x divided by 3. And if you're not sure, let's call this g of x. You can put that on Desmos, and you'll be able to see the difference. And then you can combine all of these things. First thing you do, if you have a bunch of things in here, you're going to first vertically stretch a by a, and then vertically shift by k. If you're going to combining horizontal, you're going to first horizontally shift by h and then stretch by b. When combining horizontal transformations written in the form like this, first horizontally stretch by the fraction and then horizontally shift by h. And horizontal and vertical transformations are independent. It doesn't matter which one you do first. Like I said before, you can put it in the form they give you, and it will be very helpful to you. All right, so it says this is our function, and we're going to graph all this. Okay, that's a lot, but let's start. So this is the original function here, and to do this, we're going to start by factoring out the inside of the function. So I can take a x, or 1/2, out here, because I need to have the b here, like on this part. And so we can first horizontally stretch by 2, as indicated by the 1/2. And remember that twice the size of 0 is still 0, so the point 0,2 will remain 0,2, but the point 2,0 will stretch to 4,0. So this is the original function stretched, and then you're going to horizontally shift by 2 units. So it's at 4 here, so we're going to go 1, 2. Here you're going to go 1, 2, and all these other ones. So this was on 4, it's going to end up on 6. And then once you get here, you still have to move it down 3. And so it's all these points now are down 1, 2, 3, so on and so forth. Lots of fun. Here's another video if you want to watch it, and like I said, there's also on Newton Alta, there's office hours, there's tutoring through the university, and you can send me a message on Canvas if you want to talk about this some more.